the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 1, Introduction, Part 10. What are the effects of strain rates on the material behavior? After considering the effect of temperature on the material behavior, we want to know what effect the strain rates have on material behavior. What is the strain rate? The strain rate is the speed of loading. How fast we load the material is given by epsilon dot. Epsilon dot equal to 1.5 means this is per second. Okay, because epsilon is delta L over L, change in length divided by the original length, and its speed is change in length over original length over time, which is second. So it's epsilon is dimensionless. Per second is epsilon dot 1.5 per second. Epsilon dot equal to 100 per second. Okay, so that's the speed of loading. We call it strain rate, how fast we load a specimen. Here we have a specimen compressive strain for steel EN52 at 1000 degrees centigrade. Notice 1000 degrees centigrade. That's the testing temperature. Okay, true stress, ton force per inch squared, and have a look at these curves. Okay, so if we have a high speed loading, epsilon dot equal to 100 per second, that's the behavior of the material. 40 per second, 8 per second, 1.5 per second. If we look at these numbers, we see that sigma, or the true stress, increases with the strain rate. Okay, as you can see here, for instance, for 0.1 strain, we get about 12.5 ton force per square inch. But for for epsilon dot equal to 8 and 0.1 strain, we get about 14.5. Okay, so here is 12.5, here is 14.5, and then again for 40 per second we get about 17.5, and then for about 100 per second we get about 20. So you see that the stress increases considerably as the strain rate increases. If we have a look at one of these curves, we see that at higher strain rates, note that the temperature also is 1000 degrees. At higher strain rates, the behavior of the material is like that. We have a strain hardening, and as we increase the deformation or strain, we get higher and higher stresses. But as we slow down the speed of loading or strain rate at lesser values of strain rates, we get the behavior is like this. So we have as we increase the strain, the stress is increased, and then we reach a point where it decreases. So here we have a strain hardening. Here we call it a strain softening. In fact, the material becomes softer because for more strain we get lesser stress. Okay, so here again even shows the effect of softening very considerably. Here is very appreciable that the softening of the material can be seen very clearly at 1.5 per second for strain rate. Okay, So why this happens? I mean, in here we have strain hardening, here we have a strain softening. Because according to our logic, as you increase the strain, the stress must increase. So why here decreases? What happens here? Not that this is true stress, not the engineering stress. Because if it was the engineering stress, it would drop. Because in engineering stress we get we have force over original area, but in true stress we have force over current area, so it shouldn't drop. And why does it drop here? For different strain rates it drops. The reason for this, we call it the point of reversal in compression. This happens in compression. For instance, in industry also, people who work in forging workshops, they observe such behavior. They say that as we work more on a material, if a material is worked further and further, the forging load decreases. It means that as we increase the strain, the load decreases. The load decreases. We want to know why this happens. Okay. Note that we have this 1000 degree here. It happens at 1000 degree. So what happens at 1000 degree at this point, which is maximum? Is a point of reversal. The behavior of the material reverses from hardening to softening. Why this happens? The reason this happens, in fact, as we increase the deformation, as we work harder on the material, or give the material more deformation, the strain increases. What happens is that I will show you later that as we deform a material, only 5% of the work we do goes to the deformation. 95% releases as heat. So as we have more deformation, more heat is released, and we have this 1000 degree here. So if more heat is released as we do more deformation, it means the temperature goes higher. Increase in temperature causes the softening of the material, and that's why at higher deformations, at higher strains, we get higher temperatures and the material softens out like this. Okay, why doesn't it happen here? It's due to the strain rate, because the speed is high in here. So what does the speed to do with the, why doesn't the increase in temperature doesn't soften this material? I said because the speed is higher. So what is the logic here? The logic is when the speed of loading is so high that the heat transfer cannot compensate, because increase in deformation, we said, causes increase in temperature. But in lower strain rates, this increase in temperature can have its effect. But at higher strain rates, because the speed is so high, the sleep systems cannot move because they need time to move. Also, the temperature, in order to influence the material, it needs time, because we don't give it time in here. We increase the load so fast that these other effects cannot happen, and in such a short time. So because we have no time in here, these effects are negligible, and we see this strain hardening effect as we increase the deformation. So that's the logic behind this curve. Now this is another figure, different figure, which we have tried to show the effect of a strain rate at different temperatures. Because in the previous figure, we just had one temperature, 1000 degree, and different strain rates and different strains. But here we have the stress and the strain rate. 40% compression for aluminum. So here the deformation is constant for all of them, but before it wasn't. At 20 degrees, of course, we see the usual behavior as these strain rates increases, nothing much happens. It means that aluminum at 20 degrees is not very sensitive to a strain rate, okay? But as we increase the temperature, it becomes sensitive, like here. At 550 degrees, we see that if we increase the strain rate, the stress suddenly increases, and we have a steep gradient here, okay? But as we change the temperature or decrease the temperature, we see that this sensitivity to strain rate decreases, okay? So that is another angle of view to the strain rate and the temperature, their combined effect on the material behavior. In this figure, we have shown a stress-strain response of a viscoplastic material at different strain rates. What is a viscoplastic material? We know what plastic materials are. Materials who deform under stress plastically. Most of the metals do. So they are plastics, and plasticity is about that. Now, what is viscosity? What is viscosity? Viscosity is to do with the fluids and the behavior of the fluids. But why we are using it for materials such as aluminum, steels, and this kind of things? For metals. Metals are not fluids. But metals, when they go to the plastic deformation, when they go under plastic deformation, and they behave like a fluid, you know, and because they flow, and that flow can be viscous. So what is a viscous flow? For instance, if you consider water, okay, what is the viscosity of water? You must compare it to the viscosity of something else, like honey. If you look at water and honey and compare them together, water flows very easily. We say the viscosity is very low, but honey flows very hard. You know, it needs more shear stress to flow. So we say that honey has high viscosity. So viscosity is a measure of flow of fluids. In metals also, if a material flows plastically, we can apply this viscosity to it if it is sensitive to strain rate. So viscous flow or viscoplastic material behavior has to do with the strain rates. So flow of materials at different strain rates, or dependence on the strain rate, or sensitivity to the strain rate, we call it viscoplastic. For instance, in previous slide I showed you here that this is not sensitive. So this is not a viscoplastic material. But the behavior at higher temperature could be viscoplastic. Okay, so we can use a viscoplastic model here, but not here. because here it depends on the strain rate. The flow of material depends on the strain rate. Now we have shown a viscoplastic material here, okay? So stress strain response of viscoplastic material at different strain rate. We have shown a viscoplastic material. Now let's have a look at this figure. We have stress versus strain. These green lines are simple stress strain curves at different strain rates. For instance, this one is at 0.1 per second and this one is at 100 per second. Okay? And this blue line is the stress strain curve with changing strain rate. For instance, we have loaded this strain curve, this blue line, with the 0.1 per second strain rate. In here, we have changed the strain rate, increased it. This is increasing, the strain rate is increasing, reaching 100 per second. So at points in between, it's between 0.1 to 100. And then we have kept it at 100 per second, and then again we have decreased the strain rate to 0.1, again increasing and decreasing like this. Okay, so this is the behavior of a viscoplastic materials, and most of the metals at high temperatures, they behave viscous and they are viscoplastics. Another effect on the behavior of material can be observed under high pressures, high hydrostatic pressures. Okay, here again we have sigma, and this we have compression test. This is percentage shortening. It means that the length of the specimen becomes shorter. So it's like the percentage elongation in tensile test. Here we have percentage shortening in compression. And as you can see, for instance, here we have 6,000 atmosphere pressure, hydrostatic pressure. It means the pressure from all over the place. The specimen is under the pressure in all directions. And here we have 8,000 atmosphere, and here we have 10,000 atmosphere. You can see how the material changes. Behavior of limestone cylinder under axial thrust and lateral pressure. So we have put a limestone cylinder, we have loaded it with the axial thrust. It means that if the cylinder is in this direction, the axial thrust also in this direction, and lateral pressure, of course, is the pressure which is hydrostatic pressure. Now, in here, you see that the material almost behaves like other materials because it reaches a maximum, a yield point, a maximum tensile strength, and then it decreases and breaks here. At 8,000, it doesn't break, but still it decreases here and reaches there. And at 10,000 atmosphere, you can see that it increases and doesn't break. Why this happens? Because pressure prevents cracks from growing. Crack growth is arrested under pressure. Okay, and the reason that the materials break or fail is due to the crack growth. Okay, so because the compression or pressure hinders the growth of a crack, that's why the material behaves like this. Okay, it doesn't let the crack to grow, and so there is no break, no failure. under high pressures. So we can, if sometimes we form a material like titanium and we see a lot of cracks in it. So if we form this material under high pressures, we won't see those cracks.